If a node in a network stops responding, you face an immediate engineering problem. Is the process dead, or is the network just slowing the connection to an agonizing crawl? From a single node's perspective, a crashed process looks identical to a perfectly healthy process suffering from a severe delay. This is the core paradox of asynchronous distributed systems. These are networks that operate without any strict timing assumptions. Messages can take an arbitrary amount of time to arrive, making it impossible to rely on a clock to determine truth. To reach consensus, for every node to agree on a single value, a system must decide whether to wait for a slow response or proceed without it. The FLP impossibility result proves that in an asynchronous system, this decision can never be guaranteed. If you wait forever for a dead node, you lose liveness. If you move on and ignore a slow node, you risk safety. This forces a strict vocabulary shift in distributed engineering. We can rarely say a node is definitively dead or crashed. We evaluate processes under suspicion, labeling them as unresponsive, faulty, or suspected. Because perfect detection is mathematically impossible, failure detection algorithms do not search for the absolute truth. They exist to engineer a negotiated, mathematical trade-off. Every failure detector is governed by two competing properties. The first is liveness. This is the guarantee that a specific intended event must eventually occur. If a process fails, the failure detector will eventually notice. The competing property is safety. This guarantees that unintended events will not occur. If the failure detector marks a node as dead, that node must actually be dead. In practical engineering metrics, liveness translates to completeness, how fast and reliably the system catches failures. Safety translates to accuracy, how precisely it avoids making mistakes. These two properties are in constant friction. Increasing efficiency by lowering the threshold to suspect a node inherently decreases accuracy. It makes the system prone to triggering false positives during minor network blips. This matrix determines the core behavior of a distributed database, specifically how long it waits before it triggers a leader election or starts the expensive process of re-replicating data to a new node. We can query the state of remote processes using two baseline methods. We can use pings, which send a message and expect a response within a specified time, or we can use heartbeats, where a node actively and periodically notifies its peers that it is still running. Under normal conditions, a ping system is straightforward. Node P1 queries its neighboring node P2, and P2 immediately sends an acknowledgement back. Nodes use these continuous responses to maintain local lists of alive, dead, and suspected processes, updating the timestamp with every successful ping. The critical vulnerability here is the reliance on a fixed time deadline. The precision depends entirely on selecting the perfect timeout interval for the network. Consider a state where the network is slow, but the nodes are intact. An acknowledgement from P2 travels incredibly slowly, arriving long after the predefined timeout period has expired, and after P1 has already sent its next message. This triggers a false positive. The active node is marked as suspected or down, despite being perfectly healthy. Fixed timeout mechanisms are too brittle for highly variable networks. To avoid these false positives completely, engineers must find new ways to detect failure without relying on a rigid ticking clock. Marcos Aguilera's timeout-free failure detector provides a structural alternative, designed specifically for asynchronous systems where time cannot be trusted. Instead of measuring time, the system counts heartbeat messages and tracks routing. Each heartbeat message app appends the ID of every node it visits into a growing path list as it travels through the network. Nodes aggregate this path data to verify states indirectly. Even if a direct point-to-point link between two nodes fails, the target can be proven alive if its heartbeats successfully route through an intermediate neighbor. The limitation of this approach is interpretation. Engineers still must pick a strict numerical threshold for the heartbeat counters to explicitly define a failure. Eliminating timeouts solves the problem of arbitrary deadlines, but the system still requires a broader, more decentralized perspective to be truly accurate. The Scalable Weakly Consistent Infection-Style Process Group Membership Protocol, or SWIM, introduces pure consensus to the process. SWIM relies on outsourced heartbeats. A node no longer relies solely on its own direct connection to pass judgment on a peer's health. During the initiation phase, node P1 sends a ping to P2. Here, P2 fails to respond. Instead of immediately marking P2 as dead, P1 begins an outsourcing phase. It enlists multiple random members of the cluster to double-check P2's state. In the verification phase, these outsourced nodes successfully ping P2 themselves. When P2 responds, they forward the acknowledgement back to P1. This accounts for both direct and indirect reachability. It gathers more information about suspected processes quickly, and it does so without the heavy bandwidth cost of broadcasting messages to every member of the network. By distributing the responsibility across the cluster, SWIM proves that decentralized consensus generates more accurate decisions than individual observation. The phi accrual failure detector replaces binary up or down states with a continuous probability scale. This is the model used in modern systems like Cassandra and Akka. The process relies on a monitoring subsystem. The system collects a sliding window of historical arrival times for incoming heartbeats, organizing them along a normal distribution curve. The algorithm calculates the mean and variance of this specific window. It uses this historical data to estimate the exact probability of when the next heartbeat will arrive. The interpretation subsystem then uses that probability to compute a specific suspicion level, represented by the value phi. As time passes without a successful heartbeat, the phi value rises dynamically. This creates a suspicion scale that continuously adapts to current network congestion and erratic arrival times. Finally, the action subsystem executes. The application sets its own threshold on the phi scale, deciding exactly how much suspicion is required to trigger a callback and mark the node as down. The phi accrual model allows distributed systems to dynamically adapt their completeness and accuracy trade-off to real-time network conditions, rather than relying on hard-coded assumptions. Another highly reliable method for bypassing a single node's limited view is gossip-style failure detection, which aggregates the state of the entire cluster. Every node maintains a list of heartbeat counters for all other members. Periodically, each node increments its own counter and merges its entire list with a random neighbor. This diagram illustrates a gossip protocol in action. Looking at the first panel, we see a healthy state where 3 communicating processes successfully increment and share their timestamps across synchronized tables. If a single link fails, the data survives. Here, node P3 cannot speak directly to P1, but P3's updated timestamp still populates in P1's table because it was successfully relayed through their mutual neighbor, P2. A true failure state only registers when a node's counter completely stops updating globally across all merged tables, as seen here when P3 drops off the network entirely. Gossip maximizes data reliability through redundant communication paths. It ensures that a single severed link doesn't result in falsely bringing down an active node. The Fuse failure notification service takes a different approach by reversing the detection problem. It intentionally converts individual process failures into group failures to save on communication costs. It operates on the principle of quiescence, using the intentional absence of communication as the method for propagating a failure signal. In a 4-node group, assume P2 crashes. P4 detects this, but instead of alerting, intentionally stops responding to pings. P1 and P3 notice the silence and cut their lines, converting the individual failure into a group-wide silence. Everyone learns of the failure. Fuse provides a highly robust failure propagation method by leveraging the one thing an asynchronous network can always rely on: the definitive absence of a message. We have traced the architectural evolution from rigid ping intervals to decentralized swim checks, dynamic phi accrual probabilities, and redundant gossip tables. In an asynchronous world, failure detection is never about absolute truth. It is always a matter of balancing completeness against accuracy. The Chandra-2-egg theorem shows that consensus is possible even if a failure detector makes an infinite number of mistakes. As long as the detector eventually identifies every truly failed node, maintaining completeness, the consensus protocol can be designed to tolerate and recover from the temporary inaccuracies of false positives. This graph plots completeness on the x-axis against accuracy on the y-axis. Pings, swim, and phi accrual all occupy different positions on this curve. Robust systems achieve consensus not by eliminating mistakes, but by choosing the right architectural model to accommodate and account for them. Distributed systems use these algorithms to navigate the gap between absolute truth and the messy reality of network timing. Understanding failure detection allows us to build reliable protocols in a world that never stops moving.